In class 9, page number 32, chapter number 2, kinematics, we have already defined vibratory motion, which says to and fro motion of a body about its mean position is known as vibratory motion. It is also called oscillatory motion, or can be defined as vibratory motion. When a body moves to and fro about a fixed point, it is said to be in oscillatory or vibratory motion, such that the motion of a swing and the pendulum of a clock shows vibratory motion or oscillatory motion. Another example of vibratory motion is mass spring system. When a mass M attached to the end of a spring, whose other end is fixed with a rigid support, and then displaced from its equilibrium position or a resting position or a mean position, it will start to vibrate to and fro, back and forth about its mean position. This is also an example of vibratory motion. Equilibrium position is the position where the object is in a state of rest. A spring is not stretched or compressed, so it will not oscillate unless we displace the object from its equilibrium position. So this is also an example of vibratory motion or oscillatory motion. The name of the chapter is simple harmonic motion. Then why we are discussing vibratory or oscillatory motion? Because this is the first condition for simple harmonic motion. We only test those objects for simple harmonic motion which are already in vibratory motion. If someone asks, is circular motion simple harmonic motion, or translatory motion is simple harmonic motion, a rotatory motion is simple harmonic motion, or a straight line motion is a simple harmonic motion, we can directly say it is not, because there is no vibratory motion, which is the first condition for object to have simple harmonic motion. So if there is vibration or vibratory motion, we will check the object is executing simple harmonic motion or not, otherwise we will not check. Before we move on to understand simple harmonic motion, we should first understand some physical quantities and definition that will help us in understanding simple harmonic motion. These physical quantities and the physical terms are vibration, time period, frequency, amplitude, and displacement. These are five related things, five related physical quantities that will help us in understanding simple harmonic motion. So, starting with our first definition, that is vibration. One complete round trip of a vibrating body about its mean position is called one vibration. To understand the definition of vibration, look at the example of mass spring system. Initially, the mass M is at rest in equilibrium position O. If we displace the mass M from its equilibrium position to extreme position A, after the release, we start to observe the motion of a mass. The mass, due to the elastic restoring force, will move towards point O, the mean position, and then it goes to point B, the other extreme position, the other side of the door, and then it will return back to the point A. This is called one vibration. Starting from point A and then returning back to point A. The motion or the condition for the object or the mass is called one vibration. You can count this from anywhere else. For example, if you are counting from position O at equilibrium position, then it is when it is returning back to the equilibrium position after the one complete round trip, then it will be its one vibration. Or if we are counting from point B, or you are looking at the point B, then returning back to point B after one complete round trip, then this will be its one vibration. So this is the definition of one vibration. Now our next definition is time period, and it can be defined as time required to complete one vibration is called time period. It is denoted by T and measured in second. To understand the definition of time period, again look at the example of mass spring system. Consider you have a stopwatch and your mass m is at point A. You turn on your stopwatch and start to measure the time. The mass goes to position O and then it goes to position B. After that it returns back to point A. Now you turn off your stopwatch. The time in your stopwatch is showing the time period of mass spring system because it is the time for one vibration, and the vibration we have already defined. Now our next definition is frequency. Frequency is defined as number of vibration completed in 1 second is called frequency. It is denoted by F and measured in hertz or second inverse. To understand the definition of frequency, again from mass spring system, now you have only 1 second. Your position will be count that how far you go or how many times you vibrate during 1 second. Let's suppose during 1 second the object goes from point A to point B. That is half of its vibration. As it's completed half of its vibration during 1 second, so its frequency is 0.5 Hz. Frequency is the reciprocal of time period. Now we are going to relate time period and frequency. Time period is a reciprocal of frequency, or frequency is a reciprocal of time period. Let's suppose the frequency of a vibrating body is 0.5 Hz. What's that mean? That the vibrating body is completing half of its vibration during 1 second. So how long will it take to complete its vibration? Time required to complete one vibration, that will be 2 seconds, because it is completing half of its vibration during 1 second, and number of vibration completed in 1 second is called frequency. So its frequency is 0.5 Hz. But as in a 2 second it will complete its vibration, then the time period will be 2 seconds. So its time period will be 2 seconds, that is 1 divided by 0.5 is equal to 2. So if we reverse the frequency, we can get the time period, or if we reverse the time period, we will get the frequency. So these two physical quantities are reciprocal to each other. Now our second last definition is displacement. The distance of a vibrating body from its mean position to any other point is called displacement. It is denoted by x, and the SI unit of displacement is meter. Suppose the object is at point O, the equilibrium position, and we start to displace it from O to any side, let's say the right side or the left side. The distance will be its displacement from point O to any side where we are taking the object. The distance it travels will be its displacement, that is the distance from point O to the point where we are taking the object right now, let's say at this point. So the distance from equilibrium position O to the point where your object is present, this distance is called displacement. Our last definition is amplitude. The amplitude is related to the displacement. The maximum displacement is called amplitude, that is the distance from mean position to any side of extreme position is called amplitude. We can say that the distance from O to A is amplitude, or O to B is also amplitude. Now the maximum displacement, the maximum we go to stretch the spring, I suppose it's now here at point A, the extreme position, and it cannot go any further. So this point, the distance from point O to the point A, will be its amplitude. It is also a displacement, but it becomes maximum, and the maximum displacement is called amplitude. This one is amplitude as well as the distance from point O to the other side, point B, is also a displacement.